10Cs, we continue linear relations and functions. Last couple lessons, domain and range, a little different, a little tricky. But again, domain and range are talking about the relation of a dependent and independent values on a graph. We're looking at the relation for the graph, which is this unit, linear relations. Functions are part of it as well. We talked, and now we're going to look at something called function notation. Please remember, functions tell us x only occurs once. That's what a function is. And a function really is a lot like an equation. So that's what I want to start with. If we take a look at page 24, function notation, well, we have worked with, through junior high, equations. Y equals left side equals a right side. Well, in this case, the big difference I sort of view function notation as, I could set up a table of values, and here there's no limiting. I can say x could be absolutely any value. Positive, negative, decimals, fractions. It's letting me put anything in for x to then result in a y value. Because y is dependent on what x is, and x can be anything. But this is referred to as a function notation now. Function notation has this function symbol, and it could be anything. It could be g at x, it could be h at x, anything. But the big difference is what's in the brackets is your x value. And it sort of pushes on you what x has to be. It tells you what to use for x. And that's the big difference. Equation, open-ended. Function notation, it's saying we have some kind of a function, but we want you to use this in the function for the x value. Different way of seeing the same thing. Y is anything because, and here's the key part, in this case, x is anything, like I just showed you. Whereas function notation, f at x, is telling you we want you to use whatever this value in brackets is for x. And what you finish with will be your y value. F at x and y kind of interchangeable. But a function notation forces an x upon us. Easiest way is to kind of start to take a look at what it looks like. If you have f bracket 3 equals 11, this is telling you what your values are. What does the 3 represent? Well, 3 is your x value. And what you get out of it, this is essentially your y value. So we know that if I wanted to, I could say the relation here is 3 to 11. Our x value of 3 relates to the 11. That's what a function notation does for us, specifically x's and y's. So we're going to look at questions that say, hey, find the function at -2. Well, what this is saying is, what do we know? We know that our x value is -2. We want to find the function at -2, so it's telling us we don't know right now what the y value is, but we know we have to use -2 as our x. We're finding the f at x value for x at -2. Whereas the reverse is true here. It says find f at x if it equals 8. Finding the fx value if it equals 8. Well, in this case, f at x is 8. That's our y value. We don't know in this case what x is, so in this case, we don't know x, but we know that y is 8. So what's in brackets is our x value, and the value it gives us is our resultant y. That's what function notation is all about. So what's important is there's two ways now of writing things to be solved for. Right now, we have an equation in two variable. Because equation equals sign, but we have two variables. We want to turn it into function notation. Well, what does function notation tell us? We want to solve for the c value for certain d values. That's all function notation is doing. It's saying we want c for certain d value because that's the second variable. That's taking two variable equation and writing it in function notation. This equation with two variables tells us that r is 1200s plus 300. Well, function notation would tell us we want the r value for a specific s using 1200s plus 300. All we're doing going from equation to function notation is taking our variable and writing it as a function, r at s. We still want the r value given a specific s value. Don't think this is multiplying. It's not multiplying, it's a function. And that's a mistake students will make. Here, we now have function notation. The function notation is given to us because we're saying we want phi for certain values of t if we go 19t minus 7. Well, if I want to write it just as an equation with two variables, an equation doesn't require you to force upon the other value. So this in two variables would just be v is equal to 19t minus 7. A of b is equal to 0.5b plus 21. This is function notation. I just want to know what a is. For 0.5b plus 21, almost the same thing. Equations and function notation. So, how does it look if we want to do calculations? Here with example 3, it's telling us f at x is 5x minus 6. If it helps, we can also think of it. The equation, the value of y, comes from 5x minus 6. But when I look at the first example, what do I see? I see that we want the function when x is 4. So we start with f at x is 5x minus 6, but I know that x has to be 4. So we want the function of 4. So I'm going to, the function at 4 is 5 times 4 because 4 is our x minus 6. So the function at 4 equals 20 minus 6, which is 14. And what does that tell me? That tells me the relation here is that when x is 4, the y value, the resultant, is 14. Same thing. F at negative 2 is equal to 5x minus 6. Well, this time, our x value is negative 2. So we want the function at negative 2 to be 5 times negative 2 minus 6. So the function at negative 2 gives us a value of, order of ops, negative 10 minus 6, change, negative 16. So what do we know from that statement? When we have an x value of negative 2, our y value is negative 16. Function simply tells you what to use for x. Question D with the decimal, it's no different. F at negative 3.2 is, just substitute in, 5 times x, but now we know x is negative 3.2. Subtract the 6. So we end up with the function at negative 3.2. When we do the math here, negative 16 minus 6 is negative 22. So we know that when x is negative 3.2, our resultant y is negative 22. A function simply dictates what to use for x. So that's the first part to this. Here's where it gets a little bit more complicated, is if you look at E and F, the big difference here is that we don't know what x is, but we know that f at x equals 4. Well, what does the resultant? That's the same as saying we know what y is. So if I go to my equation, or my function, f at x is 5x minus 6, what do we know f at x is? F at x is 4. So that's my resultant for 5x minus 6. I don't know what x is, so I have to solve it with a little bit of algebra. Add 6, divide by 5, and x is equal to 2. So what does that tell us? That when x is 2, what's our y resultant value? It's that 4, which was what we started with this time. We knew the y, or f at x, was 4, so we use that to solve for the x. Same thing over here. F at x equals 5x minus 6. Well, we know that f at x is negative 21, so we know our resultant is negative 21, but we don't know what the x is in this case. Add 6, negative 15 equals 5x, divide by 5, x equals negative 3. So what does that tell us? That when x is negative 3, what was our initial y value? F at x, or y, was negative 21. So negative 3 results in negative 21. Functions simply dictate what the x value can be or what the y value, the entire f at x, is. And we can use it to solve accordingly. But not only because relations and functions can be presented different ways, which goes back to the first lesson, we can come up with values not in equation form, but on a graph. When I have a graph and it says f at 2, well, what is this telling us? This is telling us that that 2 is our x value. And we want to know when f or x is 2, what's the y value? So we can go to the graph. The first one, we have the x value is 2. Well, where does that hit the graph? If I go up, I see that when x is 2, my y value is 5. So I know that when I have an x of 2, it's related to the 5. And I can get that from the graph. The next one, it says f is negative 3. So we know we have the x value of negative 3. So I can go to negative 3. And from negative 3, what do we want? We know that we have negative 3. The question's saying, what's the y value? Well, when x is negative 3, I can go up to my graph and see that when x is negative 3, well, there you go. Y is 10. So we have negative 310. What about when f is 0? 0 is still a number. Our x value we know is 0. So when x is 0, there's where it meets the graph. What's the y value at? The y value is at 1. So f at 0 is equal to 1. Because when we use x at 1, it gives us y value of 1 on the graph. But this next one you have to be careful of, because this next one, what's the big difference? Well, technically, they've given us not the x, but the y, the resultant. So we know our resultant is 5. We have to figure out what's the x value. So, just so it's easier to see, take that off the graph. We now know that y is 5. Well, when y is 5, what x value gives us that y value of 5? Well, look at that. We actually have 2 parts on the graph that have a y value of 5. So if I go down, what's the x value that gives me a 5? 2. So we have 2, 5 as one of the relations. But y equal to 5 also is a resultant of an x value of negative 2. So negative 2, 5 is a second relation. So negative 2, 5 and 2, 5 represents the relation when our y is a 5. So that's what we're looking at doing. Understanding, are you given the x or are you given the y, and solving accordingly. We can do it algebraically, or we can use the graph. If we take a look at the second part of this one, it says if the above graph is the function f at x equals x squared plus 1, calculate f at 2. Well, that means algebraically, I want f at 2 for x squared plus 1. What does that mean? That means my 2 needs to be plugged in because what's in the brackets is x. So f at 2 will equal 2 squared plus 1. 2 squared is 4 plus 1 is 5. So f at 2 equals 5, which means when x is 2, y is 5. That's what we had algebraically, and that's what we had from the graph. 2, 5 from the graph, 2, 5 algebraically. Function notation. So, example 5. Practice a couple. Turn the video off. Substitute in. See what you end up with. Go. So here we go. In this case, g at 2, what did that give us? It gives us x. So we know g at 2 will be 3 times 2 squared minus 2, because I want 2 in for x. So order of ops, 2 squared is 4. 3 times 4 is 12. We get 10. So we know when x is 2, our y value, our resultant is 10. If I use negative 4, still, g of negative 4, same function. Well, that's going to be 3 times negative 4 all squared, subtract 2. What does that give us? Well, 3 times negative 4 squared is 16, minus 2. 3 times 16 is 48. 48 minus 2 is 46. So we get g at negative 4 equals 46. So we know that when x is negative 4, our y is 46. Now, what's the big change with these next two? Well, hopefully it jumps out at you and you notice it. This time we don't know x, but we know that g of x is 25. So we had the function, and I'll just rewrite it since I've lost it. G at x equals 3x squared minus 2. But we don't know x, but we know that g of x is 25. So g of x, 25, is 3x squared minus 2. Know what value is given. We don't know x, but we know the g at x or y value. So what am I going to do? I'm going to add 2. 27 equals 3x squared. What do I do now? I divide by 3. So what do I have? 27 divided by 3. 9 is equal to x squared. How do I get x by itself? I square root to get rid of squared. So in this case, squaring x squared, square rooting x squared gives us x. Square root of 9, careful, what can I multiply by itself to get 9? Positive or negative 3. So now try this next one. Here we have, again, g at x is 1. Well, here's the same function, but this time g of x is 1 instead of 25, so we have 1 equals 3x squared minus 2. What does that mean? That means we need to solve for the unknown x. Add 2, we get 3 equals 3x squared. Divide by 3, 1 equals x squared. How do I get x by itself? Square root. So x, when I square root 1, what times itself gives me 1? Positive or negative 1. So there's function notation. You're given a function, but it sort of sends you in the direction of what to use for x and y. You'll see on page 25 that you can have situations that are quote-unquote real world. Here it says the distance a blue whale is from the shore is given by the function f at t equals 5t plus 37. So how far away the whale is based on this function. What's the position of the whale at the beginning? Well, what this question is saying is that, don't forget that t is time in seconds. So at the beginning, what do we know? At the very beginning, time is 0 seconds. So we want the distance the whale is at a time of 0. F at 0 means 5 times 0 plus 37. Because t is 0, so function of 0, and we plug 0 in for t. Function at 0, 5 times 0 is 0, plus 37 is 37. So function at 0 equals 37. It's telling us when x or time is 0, it's 37 meters from the shore. 37 meters away at time 0. Another situation, what's the position of the whale after 15 seconds? Well, position of the whale, this time we know we want time of 15 seconds. So f at 15 is going to be 5 times 15 plus 37. Because it's dictating a time of 15 is what we put in. So f of 15, 5 times 15 is 75. 75 plus 37 is 112 meters. So what is this telling us? That at time of 15 seconds, the whale is 112 meters away. The function tells us as a way of writing so we can identify the information. The last one, the time when the whale is 142 meters away from the shore, well, this time we know the distance. So the function for a certain time, we don't know the time in this case, but we know that it's going to end up 142 meters away. So if I have f at t is 5t plus 37, this time the function for some certain time we know is 142. 142 is 5t plus 37. And we want to figure after how many seconds it's that far away. Subtract 37 from both sides. We end up with 142. Subtract 37 is 105, equal to 5t. Divide by 5, and 21 is equal to t. So after 21 seconds, it's 142 meters away. Know what your function is, but besides knowing what your function is, it's important to know what the values represent. At the beginning, t was 0. That's what we used. After 15 seconds, oh, we knew t was 15, so that's what we used. The last one, we didn't know the time when we knew how far it was from shore, so we knew the function at a certain time, so that's what we plugged in for f at t and then solved. Function notation, different way of writing equations. There's your textbook assignment. Again, this is not a particularly complicated concept in my opinion, but it's new and different. Practice it, check answers, but do the work. Have fun.